So I wonder, let's go back over here for just a second. Here we had our arithmetic or linear kind of behavior, right? And we observed that we came up with a formula. When I told that story about Gauss, we came up with a formula to come up with a partial sum. In other words, when you start adding these terms together. So let's see if we can come up with a formula that will work for the geometric pattern. A formula that will work for the geometric pattern. Okay, so here's a real quick proof of this, if I can remember it. Oh, they'll move the camera. They'll move the camera, won't they? Camera. Got to move the camera. Thank you. Okay. He disappeared. Okay. Let's see if he's going to move it. There we go. Thank you. Okay. Okay. So let's say I take and write out a partial sum. So I'm going to have a sub 1 plus a sub 1 times my common ratio, right? That's my next term. And then the one after that is a sub 2 r squared plus dot, dot, dot. And that keeps going until I get to that nth term, right? Partial sum means the sum, right? The sum of the first n terms of the sequence we have. So when I get out here near the end, at my nth term, I'm going to have the first term and my common ratio to the n minus 1 power. That's my last.
Okay, so that second one is wrong. It should be a sub 1 r squared, right?
No. It's always, we're on the second term. First, second term or second element, third, and the exponent on r is 1 less than the term you're on.
Okay, so next one's going to be a
Look at the formula.
r cubed.
Raised to the n minus 1 power. And notice the pattern. Let's come back here for a second. Notice the pattern in our example that the power of the common ratio is 1 less than the term you're on. Everywhere. That led us to this generalization here. So the power of the common ratio, the exponent on the common ratio, is going to be 1 less than the term that you're on. So when I now,
But that's not the same up there.
excuse me?
How, I don't see the pattern the same way up there. You've got a sub 2, and then it's exponent
Oh,
of 2.
I'm sorry. That's a typo.
Oh. So what should it be?
What, well,
A
you tell-
sub 2 to the
you,
radical
no, hold
1,
on. Sorry.
right?
You're correct. But what's wrong with this? That's a typo.
Should it be a
You
1?
have 2 a sub 1s.
That should be a 1. Thank you.
Okay.
Thank you.
Okay. Now I'm fine.
Boy, I don't want to make a mistake on these videos. Man, the whole world will see them. Okay. Thank you for catching that. I'm sorry
And some
for.
student will be completely
Okay.
confused.
What I thought you were bothered by was the exponent on the r.
Okay, so the next one should be a sub 1 r cubed.
Yes.
And then
Okay.
a sub 1 r.
And then if I'm going out to the 10th term,
It'd be
then this is going to be a1r to the 9, right? Okay, now we're good. Thank you for catching that. Okay. Everybody good? Okay. Now, let's see if I can remember this proof. Let's say I multiply this partial sum. Here's a sum of terms, right? Sum of terms. And matter of fact, in sigma notation, this would be k equals 1 to n, and I'd be taking a sub 1 r to the k minus 1. So there's my summation or sigma notation for this partial sum of n terms.
Okay.
Feel good? If I took outside in front of this and put a multiplier of r, then every one of these terms here would be multiplied by r, wouldn't it? Wouldn't they? Okay. Everybody hear that? If I multiply this partial sum by r, then there's going to be an r multiplier on every one of these terms because we would distribute that common multiplier to each of these terms. Let me multiply by minus r instead. If I multiply by minus r on the partial sum, then I'm going to have this term times a minus r, right? And what I'm going to do is I'm going to put it right here. A sub 1 times minus r, and that's going to make that term negative, isn't it?
Yeah.
Okay.
Is that going to make both of them negative?
Well, I'll tell you what, I'm just going to write it. And you'll see that what's going on. So I'm going to have minus r a sub 1 minus, see it?
Well, that one's going to be positive because r times
Hold
r.
it. No. Keep the
Oh,
r.
okay.
You with me? Okay. So minus r times this is going to be minus a sub 1 times r, right?
Squared. Yeah.
And so that's going to be a minus r squared a sub 1, right? Or a sub 1 r squared. Let me leave it that way. Matter of fact, let me leave this one in that order. Okay, times minus r, and then a minus a sub 1 r squared, and a minus a sub 1 r cubed, right? And then I keep on going, and then I get to this last one, I multiply it by minus r,
Negative a sub 1 r.
and on that last one right there, I get minus a sub 1 r to the, if I multiply this times an r,
2n.
here, watch this. Right? If I and there's a minus sign out in front of that, what do you get right there?
Minus 2.
You add those exponents, don't you? Don't you get r to the n right there? You're adding these exponents,
Just
and
then.
you get,
Just then.
right? R to the, right? Okay. Now, let's add this to this. So we have s sub n minus r times s sub n, and that's going to be equal to, look what happens over here. These terms subtract out, don't they? All those inner terms subtract out. And a matter of fact, what's the term that's just before this tucked in here that I did not write?
That.
This thing, one less than that on the exponent, right? And that's going to cancel with that guy. And so what you're left with is all this stuff reduces out, and you're left on the right side when you add this mess to this, you're left with a sub 1 minus a sub 1 r to the n.
And then do you factor?
Okay, and remember what we're trying to do. We're trying to come up with a formula for a partial sum. A formula for a partial sum. And this is kind of a tricky proof. It's kind of a tricky proof. So what we did is we kind of finessed this by doing this little trick, by multiplying both sides of this partial sum by minus r, and we got this, and now we're adding this to this, and we ended up, everything reducing, and we ended up with this. And notice on the right side here, there's a common a sub 1 you could factor out. And over here, there's a common s sub n we could factor out.
And we're trying to solve for s sub n, right?
Yeah.
Okay.
Thank you. We're trying to solve for s sub n. To come up with a formula for the partial sum.
So then you just have to divide by 1 minus r.
Excellent. You got it. So we have a sub 1 times 1 minus r to the n over 1 minus r. Ah, there we go. And this is equal to, in sigma notation, where our index is 1 to n, of this a sub 1 r raised to the k minus 1. There we go. So this is the sum of the first n terms of a geometric sequence.
And this is all going to sink in next term, right?
Eventually, yeah. over the holidays, you know, after this term's over,
Yeah, I'm sure while I'm rolling out cookie dough, this is going to sink
yeah,
in.
while you're rolling out cookie dough, keep thinking about these things and going, oh, that geometric pattern as I build my cookies and collection.
I've been dreaming math.
Good, okay. This is called the nth partial sum. So similar to the arithmetic sequence and series, we have now a formula for the nth term of a geometric sequence, and we also have a formula for the sum of n terms of a geometric sequence. Whew. Okay. Do you see the exponential behavior sitting here? Related, it's not, remember, these are not continuous smooth curves. Okay? But the base here is r, but we call that a common ratio. And if that ratio is smaller than 1, like we saw in our example, then it's a decay exponential. Good. And if that r was bigger than 1, like we saw an example of 2, it's going to grow exponentially in its kind of pattern. Okay, so anyway, you got a couple formulas. Let's look at an example. Let's actually look at an example now of this and see, actually, why don't we take that same example we just did? Yeah, Alyssa?
When we plug numbers into that equation,
Yeah.
since the top and bottom are both binomials, can we cancel the bottom one out
Oh,
and subtract n by 1?
this is a power of n, though, on that, exponent of n. So things don't just cancel out in there. Don't violate basic rules of exponents, okay, or of fractions, of cleaning, how to clean.
N happens to be 2, then you could take the constant.
Yeah, if n was 2, you could factor. If n was 2, good observation Melissa made. If n was 2 here, you'd have this would be a difference of squares then, wouldn't it? 1 minus r squared, and you'd be able to factor and reduce. But in general, n is some power, right? Yeah, you can't just knock that out of there. Okay. So, related to what you just asked is, let's take our same example where we had a sub 1 was a 6 and our common ratio was a 1/2. And let's see what would happen if we wanted to find out the exact value of s sub, say, 10. 10 terms. 10 terms.
And we're starting at 6?
First term given to us, a half. In other words, we have a pattern, which is on the previous board. 6, 3, 3/2, 3/4, 3/8, 3/16.
Well, then it's going to be
Okay? And what we could do is we could just take our calculator and add those together, couldn't we? For 10 terms. Couldn't we? But what if I said I wanted s sub 90? You could very primitively add all those numbers together with your calculator and end up with an answer, but that's not really a very sophisticated approach, is it? 90 terms. Okay, so let's use the general. See, this fits for any geometric pattern, doesn't it?
Why is it called geometric? Does it have to do with shape?
You know, I believe it does, but I don't know what that is. Relates to, and almost everything, actually almost everything in at least the level of mathematics you've seen so far can be related to geometric analogies. And I'm not sure the history of this, and maybe the origins of this were geometric. As a matter of fact, there might even be some applied problems in our book that sort of show us geometric patterns. There are pyramids and things like that that might behave where each row, maybe in a concert hall, each row is multiplied by a certain number to get the number of chairs in the next row. See? Maybe by 1.1 or something. and you're going to expand and to build a concert hall. You know, so there's all kinds of things. Or you're going to stack bricks on each other and stuff like that. So there are geometric patterns that would definitely relate to these kind of things. And that may be the origins of that word being used. So grabbing our formula then, we're just going to drop in the first term, and we're going to put in our half values right in here, and we have to know how to clean these things up, which means you have to be fairly good with fractions. So let's see how good you are with fractions. We're going to have 6 out in front, and we're going to have 1 minus a half raised to the 10th power divided by 1 minus a half. Right there. If you're watching the video, just pause it, see if you can clean this up without touching your calculator. See if you can clean that up without touching your calculator. Okay, so let's continue on right now with it. S sub 10 is going to be equal to 6. Let me fix this a little bit. And I may have to actually move to a different spot on the board here. 6 times 1 minus 1 over 2 to the 10th. Ignore this mark. That's on the board here. Okay. Matter of fact, I'll do that. Over 1 minus a half is 1/2. Okay. Invert and multiply. Right?
Why did that 10 move down? I'm a little confused there.
1 to the 10th. Go back to your rules of exponents. I'm glad you asked, because other people will have the same question. 1 to the 10th over 2 to the 10th. 1 to the 10th is still 1. Whoops, sorry. 1 to the 10th is still 1, and 2 to the 10th is right there. Okay. Then you could also invert and multiply this half, couldn't you? Invert and multiply times 6 and get 12. Okay. And now what I'm going to do is come up here on the proof, erase some of this so we can wrap this up here.